Today we're going to look at some financial models, and these models are in the form of an exponential function. Because of that, depending on what variable we're looking to solve for, we may need to use a natural log or a logarithm to help us during that solve process. We'll start out by looking at how much money will I have in the future given a particular principle. We'll look at effective rates of return, which is essentially asking how do I earn money the quickest. We'll also look at a present value of a lump sum. So let's say in 10 years you want to have $50,000. How much money would you need to put in the bank now? And then last we'll look at how long does it take to double my money. All of these ideas are really formulas that are expanded from the simple interest formula. So you remember the simple interest formula is just principal times rate times time. T is listed in years. Now you can borrow or lend in months. You'll just need to convert it to a fraction of a year. And when we're looking to figure out how much money we owe back, we'll have to find out what our interest is and then add that back to the principal. So if I were to borrow $100 and I have that at 5% interest out for 3 years, I would need to pay back the full $100 plus my convenience fee, if you will, for the interest. So I would need to pay back the interest that I would find by multiplying 100 times a 0.05, right, because I need to change my percent to a decimal, times the 3, and I would get 15. So I would need to pay back a interest fee of $15 plus the 100, so I have to pay back $115. And so you might say, well, that's not so bad. Well, $100 is not a lot of money to borrow, and 3 years is actually not that long of a period of time if you think about mortgages usually being 30 years or cars being 5, sometimes 6 years at much more than $100. But when you borrow money in the real world, it's very rarely lent out at a simple interest formula. Normally, it is borrowed out at a compound interest formula. So you can see that it's a little bit more complex. You still have P being your principal, and R is still your rate, and T is still time, but now I have this N component for your compounding. So instead of just ending on your fiscal year and say, all right, 1 year has passed and this is how much has accrued, we're going to stop at a couple of different intervals along the way during that fiscal year and calculate interest and add that on. So what does this look like? If I was compounding annually, that's kind of my compound interest formula that we saw before, only now my interest will be earning interest and my N would be a 1. Semi-annual, sometimes biannual, is going to be compounded twice a year, so I'll stop halfway through my fiscal year, find some interest, add that on, and then keep adding on some more. Quarterly, we're going to add interest 4 times a year, monthly 12, daily 365, and there's actually one more called continuous that we'll look at in a minute. We're going to start with these. So let's look at our $100 again. If I said now that my interest was going to be compounded, so not a simple interest where you just pay the interest earned on that $100 every year. And I'm going to put simple up here. That was $115 that we would pay. If I said, well, I'll lend it to you, that $100 for 3 years, but I'm going to compound it annually. And what does that mean? That means now, at the end of the year, I'm going to say, well, how much money did they have out and for how long? And I'm going to start tacking on my interest every year. So the first year, you would still only owe the $105. But then the next year, that interest, that $5, is also going to start earning its own interest. So N is 1, and then I have 1 times 3 up here. And so the value, if I borrowed $100, 1 plus a 0.05, now raised to the 3, would be 100. 1 plus 0.05 raised to the 3rd. Well, now I have to pay back $115.76. So I got a little bit of extra money by charging you compounding interest annually instead of a simple interest? What if I wanted to earn my interest even more frequently and have you pay me more often and did semi-annually? So semi-annually, I would still have the 100. It would still be 1 plus a 0.05, but now it will be divided twice a year. So when you have compound interest, it's not 5% every single time. I get a little piece of it each time I go. 2 times 3. So now my exponent will be a 6. I'm going to go in and say second, enter. So that I get the last piece that I put in. I'm going to change this to divide by 2, raised to the 6, so that we don't have to type it all over again. And now I get $115.97, even a little bit more. So you see the pattern. What about quarterly? Change all my 2s to 4s. Second, enter. Change my 2 that's in my denominator to a 4. Instead of being raised to the 6, it's now raised to the 12. $116.08. Monthly, 0.05, divide by 12. 12 times 3 is 36. Second, enter. 12 raised to the 36. Even a little bit more. 116 times $116.15. Now finally daily, my denominator will be a 365. Now my numerator, or my exponent, is 2 times that. So if you find yourself in a situation where it's not a number that you could just kind of multiply off the top of your head, make sure that your exponent is inside its own set of parentheses on these older version of the calculator. On the newer version, it's much easier to see that it's up in the exponent. With the older ones, it's not quite as easy to see. So 365 times 3, because I'm talking about over 3 years, and that's $116.18. So it's the same amount of money, the same interest rate, but the changing how often you compound that interest made that interest accrue faster, and there was more of it. And so even though the changes were very small, about $1 or $1.50 worth from simple all the way to compounded daily, that's with a very small amount of money. If this was $100,000, the difference would be much bigger, even though it grows at that same rate for every 100. So for every 100 you borrow, the difference would be about $1 in between from your simple to your daily. But you're probably not borrowing $100. You may be borrowing $100,000. And so now that difference is going to be $1,000 if all of these hundreds or thousands. What if we had something that was compounded continuously? Well, continuous compound is something that, as it describes, doesn't have a stop point where you say, oh, I'm going to add interest now and calculate it and then just let it sit. It's a process that continues the whole time. We tend to see continuous growth in nature, like if you're looking at bacteria or the population of a country, something that doesn't just happen one time a year when you just happen to have counted it, but something that goes on along that whole process. Notice that the compound interest formula has the number E in it, right? That's not a variable, that's our number. We'll still use P for principal, R for rate, and T for time. And the time could be whatever you need it to be. But if I was going to borrow that same $100 and compound it continuously over the 3 years, I would have 100 times E raised to the 0.05 times 3, and I would have to pay even more. Not much more, right? About a thousandth of a penny, but that was only on $100. So that difference is going to get multiplied by whatever your difference is out in the front. So if this was 1,000, you would see that it's the same numbers, just moved over one spot. And so now that difference becomes much bigger, even though the rate of which it's changing is the same. What if you wanted to find which one would give you the most money the fastest? Well, you can use the effective rate interest formula, which is kind of just a fancy rewrite of what you had on the other screen. What you kind of do is pretend that you're just going to be investing $1, because the rate of which $1 grows is going to happen to all those dollars equally. So even though the interest grows faster, it's going to go faster on each individual dollar. So the real way to earn a lot of interest, quite frankly, is to start out with a lot of money to earn interest on. If you wanted to buy a 5-year CD, a certificate of deposit, which is kind of like a fancy savings account, American Express says, I'm going to give you 2.15 annual interest compounded monthly. First Internet Bank says, I'll give you 2.2, but I'm going to compound quarterly. And Discover says, I'll give you 2.12 compounded daily. Which is the best one? Which bank should you choose to go with? What we're basically going to do is pretend that I'm going to invest $1 and plug that into each of the compound interest formulas that match the bank. So American Express says, I'll compound it monthly. First Internet said daily. I'm sorry, quarterly. And then daily was Discover. So if I was going to put $1 in that account, that would be my principal. This one inside of the parentheses is a part of the formula. Here's your interest. Now let's pretend we're going to let it sit for 1 year. So 12 months, and then we're going to let this go for 1 year, so 12 times 1. This is how much money I would have in there at the end of the year. I'm going to take my $1 back out, and I'm left with the interest. And so my effective interest rate is 2.171. What that means is, if you wanted to find a bank that paid you in simple interest, you would have to find a bank to pay you this much interest compounded using the simple interest formula to get the same amount that American Express will give you. They're compounding at 2.15. They would have to compound at 2.17 because when you're compounding monthly, that's 12 more times than it would if it was just annually at the one time at the end of the year. So a lot of times you may see something like AYP, like annual yield percent, and it's always higher than what the percentage that they're paying out on the actual account is. That's the effective rate. It's saying this is the same as if I was going to pay you the 2.17, but it's 2.15, and we're just going to compound it. First Internet Bank said it would be even a little bit better, 2.2 compounded quarterly. So we're going to only go 4 times a year, but they're giving you a higher rate. Does that work out better? Yes, because if I put $1 in here, at the end of the year, I'd have $1.02 and then a little bit more. Take my dollar back out, their effective rate is 2.218. So much higher than the 2.171, although it doesn't look that much higher in your interest. Discover says, well, I can't beat those two. I can't beat American Express and Internet Bank, but I'll compound you daily. And you might say, oh, that's going to be really good because daily means they're going to compound more often. But this interest rate is so much lower that once you figure it out, it's actually the lowest of the three. And so which one should you choose? Well, if you want to earn money the quickest, you want to go with First Internet Bank. That's how you're going to make the most money. If you want to figure out how much money you need to put in now so that you have a certain amount later on, you can use the present value formula. So if I want to have $1,000 in 10 years, how much money would I need to put in now? What this formula is just a rewrite of the other. So if I had originally the amount that you have out is the principal times 1 plus r over n to nt. And I want to now solve for this because I know how much money I want to have. I need to figure out how much I need to put in now. I'm just going to divide this off on both sides, which leaves me with that 1 plus r over n to the nt in my denominator. And the way that you can bring a denominator up so that you don't have to have it underneath is to raise it to the negative exponent. And so it's the same exact formula, you're just looking for a different part of it. So if you start with the original one that we had been looking at, where it's your future value, you could still just crunch this number from the 1 plus r over n to the nt and then divide it off on both sides. Or you can rewrite the formula first and find out how much money you would need to put in. So if you were earning 7% compounded monthly and in 10 years you wanted to have $1,000, you would have to put almost $500 in now in order to get that amount of return. If they were to do this compounded continuously, you would rewrite the PE to the RT, except now instead of dividing off 1 plus R to the N over N, it would be E to the RT. Again, the exponent is in the denominator, so the way you pull that up is with a negative exponent. And so 1,000 E raised to the negative 0.0610, and you can put your negative inside of the formula either on the 0.06 or on the 10, and you would need to come up with a little bit more given that the interest rate is a little bit lower than it was on the other problem.